Okay, this is the video lesson for discussion 5.2, which focuses on types of chemical reactions. So we'll be identifying types and then also using that information to predict the products of a reaction. Okay, so first, just to make sure we're all talking with the same vocabulary, just to make sure you know that reactants in a chemical reaction are to the left of the arrow, and these are consumed by the reaction, and products are to the right of the arrow, and hence the name they're produced or created in the reaction. So in this imaginary reaction here, the reactants would be A and B, the products would be C and D. I assume you all know that, but just making sure we're on the same page. Now, one thing you probably have seen as you see more and more reactions written are something called state symbols. So state symbols tell us the state of matter of a reactant or a product. So S is for solid, L is for liquid, G is for gas, and AQ means aqueous, which basically just means it's dissolved in water. So some examples that are commonly used. So if we had liquid water, we would say H2O, liquid, and we put state symbols in parentheses, subscripted after the entire compounds. We would never put it in the middle, but just at the end. Salt, like table salt, would be NaCl solid. Carbon dioxide would be CO2 gas. Now, if we have salt dissolved in water, we would call that aqueous. Sometimes when people see a solution of salt water, they're tempted to say, oh, well, I see that it's a liquid and I know it's salt, so I'll call it sodium chloride liquid. Liquid and aqueous are very, very different. Liquid sodium chloride would imply that you took a solid and melted it. So that would be an incredibly high temperature. That would be molten salt. That is not the same thing as salt water. So you have to be a little bit careful with the use of liquid versus aqueous. One clue if you're trying to write an equation from words is that a lot of times when we have an aqueous mixture, it'll say a solution of something. That's another way of saying an aqueous mixture. Okay, so our first type of reaction is a synthesis reaction. And in a synthesis reaction, two or more reactants come together to form a single product. So the example we have here is the synthesis of potassium bromide from potassium and bromine. Now, a couple things that you might immediately notice is that bromine as an element is Br2. We'll talk about that in just a minute. But what's interesting here is that we have potassium combining with bromine, Br2, and yet the product is KBr rather than KBr2. So let's talk about the reason for that. When we write the product of a synthesis reaction, we have to consider the ion's charges. So potassium has an ion charge of +1 because it loses one electron to have the same configuration as a noble gas. And bromine has an ion charge of -1 because it gains one electron to have a configuration like a noble gas. So what that means is that based on the charge, to have a charge-neutral ionic compound, we need one of each. So currently, this is an unbalanced equation. To get the same number of atoms on both sides, we could balance this equation with coefficients. Now, during this discussion, we are not going to balance the equations with coefficients. We are simply focusing on predicting the products. However, that is how we would observe the law of conservation of mass, by balancing the equations with coefficients. So in that case, we would put a 2 in front of potassium bromide to balance the bromine, and then a 2 in front of potassium to balance that. All right, so let's talk about this Br2 issue. So we have something called diatomic molecules, and these are basically elements that when they occur as elements, they're always paired with another atom. Okay, so like hydrogen doesn't just exist as H, it exists as H2. Okay, and so this is a list of all of the diatomic molecules. You do need to know these. There's a couple different tools you can use to remember them. One is Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, or you can remember HON, H-O-N, and the halogens. Okay, so whichever you need to do, but anytime they're on their own, they get a 2. Now this doesn't apply when they're in a compound. When they're in a compound, you still have to use the charge to figure out what the subscript will be, but when these are on their own as elements, that's when you'd give them a 2. Okay, so let's look at some examples of synthesis reactions. Now, in our first example, we're going to combine iron with oxygen. Now, here, if I were asking you to predict this product, I would have to tell you the charge of the transition metal because there's multiple possible charges. So here, let's assume that iron has a +3 charge. Okay, so to figure out the formula of the product, we have to say, okay, iron is +3. We know that oxygen's ion charge is -2 because it gains 2 electrons to be like a noble gas. So what that means is that I need 2 irons to balance the charge from 3 oxygens. So the formula of my product would be Fe2O3. Again, if I wanted to have the same number of atoms on both sides of the equation, I would then balance this equation with coefficients. That's just not our focus right now. Okay? Now let's look at the next example. Now, I really suggest that when you're working on these, it's helpful on the left just to jot down the charges, because then you're not just trying to figure it all out in your head, you have something on the paper. So when I combine magnesium and nitrogen, I again have to consider their ion charges. So magnesium loses 2 electrons to be like a noble gas, so it has a charge of +2, and nitrogen gains 3 electrons. Okay? So we need 3 magnesiums to balance out 2 nitrogens. Now, when I look at this formula, I can easily balance this equation by putting a 3 in front of magnesium on the left side. It just so happens that nitrogen has the same subscript on the reactants and the product side. That is merely a coincidence, okay? That's just how it happened to work out in this case. Okay, so try these next 3 on your own. Pause the video for a second, and then you can check your answers on the next, when you press play. Okay, now, be careful that you're not just bringing over subscripts. So if you wrote NaCl2 here, what that means is that you're forgetting to look at the charges, okay? So make sure that every single time you're identifying the charges of the ions and then figuring out how many of each you need to make a neutral ionic compound. Okay, let's look at decomposition reactions. This is sort of like the opposite of synthesis. So in this reaction, we have potassium. So in this decomposition reaction, we have one reactant breaking down to form 2 or more products. So we have potassium bromide breaking down into bromine and potassium. Now, with decomposition reactions, anytime you're predicting the products, you can assume it just breaks down into its elements. The only trick here is that you have to remember when you have a diatomic molecule that you have to write it with a 2. Everything else that's not one of those 7 diatomics, you just write the element symbol as is, okay? So KBr would break into Br2 plus potassium. Now let's look at a couple of examples here. In the first one, we're breaking down liquid water, which you guys did in Lab 5-2, and it breaks into hydrogen and oxygen gas. Now both of these are diatomics, so they both get a 2. And again, it's not balanced with coefficients. We could certainly do that, but we're not going to right now. Now I want to skip the next 2 and go on to the last one on your paper. So this is the decomposition of calcium carbonate. Now, when this decomposes, it decomposes into calcium oxide and carbon dioxide gas. You might be wondering, how on earth would I expect you to know that? I wouldn't. The only reason I'm giving you this example is to show you that there are plenty of decomposition reactions where it doesn't just break down into elements. However, anytime I'm asking you to predict the products, you can assume that it does. I would expect you to be able to look at this full equation and identify it as a decomposition, but I would not expect you to predict those products. Okay, so try to predict the products of those 2 equations, pause for a minute, and when you're ready, press play. Okay, and again, the main thing here is just to remember the diatomic molecules. And if it's not one of those 7 diatomics, you just write the symbol. Okay, our next type of reaction is a combustion reaction, and this occurs when a hydrocarbon reacts with oxygen gas to produce carbon dioxide and water vapor. Okay, so people want to say that anytime there's fire, it's combustion, but combustion is a really specific kind of fire. Okay, so it has to be a hydrocarbon reacting with oxygen to be considered a combustion reaction in this definition. So our first example is the combustion of methane. So methane reacts with oxygen gas to produce CO2 and water. Okay? Predicting these is cake because they all make the same product. Now, as you might recall from 5-1, the challenge with these is balancing them, but again, that's not what we're doing right now. But as a reminder, you would try to balance these in the order carbon, hydrogen, oxygen for best results. Okay, single replacement reactions. So in a single replacement reaction, one reactant that's by itself as an element replaces a reactant that is bonded. And they have to replace atoms of similar types. So cations replace cations and anions replace anions. Let's look at a few examples. So if we have magnesium reacting with copper sulfate, copper 2 sulfate, we know that magnesium has to replace the copper because they're both metals. So copper is going to go on its own, and then we have to combine the magnesium and the sulfate. So again, just like we did with synthesis reactions, we're going to have to consider the charges of both of those ions. So we know that magnesium has a +2 charge, and hopefully you know at this point that sulfate has a charge of -2. So we only need one of each ion, so magnesium sulfate MgSO4 is the other product. Now in the next example, this is something that's a little bit different looking because zinc is reacting with hydrochloric acid, and you might be looking at this and thinking, well, hydrogen and chlorine are both nonmetals, so how do I have a cation? Well, it's an acid, and acids dissociate into ions when they're in solution. So hydrogen acts as a cation. Now the reason that you would know that hydrogen is the cation is that it's written first in the equation. Okay? So zinc will replace hydrogen, and zinc will have a +2 charge, so it'll combine with chlorine to make ZnCl2, zinc 2 chloride, and hydrogen gas. And again, because hydrogen is a diatomic, it gets a 2. Okay, try the next 3, and then we will check your answers. For the copper and silver chloride, you can go ahead and assume that copper has a +2 charge. Okay, so these are the answers. Make sure that you're really reviewing those polyatomic ions if you need to. Those are going to continue to come back again and again and again, so it'll really be worth your time to learn them correctly. Now, single replacement reactions don't always occur. Sometimes they occur and sometimes they don't. So let's look at 2 examples. In order to figure out whether they occur, we're going to use an activity series of metals. Okay? So this is arranged from most reactive lithium to least reactive silver. So the rule is a more reactive metal can replace a less reactive metal, but not the other way around. So more reactive metals are more stable when they're in compounds. So for very stable metals like silver, for example, they're fine to be on their own and not part of a compound. But something that reacts really violently, like lithium or sodium, again, is much more stable in a compound. So when I look at these 2 examples, magnesium with zinc nitrate and magnesium with lithium nitrate, I have to look at the metals and ask myself, is magnesium more or less reactive than the other metal? So in the first example, magnesium and zinc, magnesium is more reactive than zinc, which means that it can replace zinc. So the first reaction will occur. In the second reaction, magnesium is less reactive than lithium, so that means that it won't occur. So our products would look like this. We'd have magnesium nitrate and zinc, and then the second one we would just write NR, and that means no reaction. Okay, our last type is double replacement. And in this type of reaction, the cation and anion switch partners, basically, with another cation-anion pair. So let's look at some examples. Now, when you do these double replacement reactions, it is extremely helpful to, on the left side of the equation, just jot down the charges before you try to write the products. Otherwise, you're pretty likely to make mistakes. All right, so be careful that you combine cations with anions. So barium can't combine with potassium because they're both cations. It has to combine with sulfate. Since barium is +2 and sulfate is -2, I need one of each to make a neutral compound. So the formula is BaSO4. When potassium combines with chlorine, I need one of each because they're +1 and -1. So the formula is KCl. All right, let's look at one more example together. Cobalt 2 nitrate and ammonium carbonate. Now this one looks really overwhelming. When you're looking at it to try to predict the products, you might feel like it just seems too hard and you don't even really want to bother and you're just going to guess. Take the time. You do know these, and so if you take the time to write out the ion charges before you try to predict the products, it actually isn't that overwhelming. So we know that nitrate has a charge of -1. we can use the charge of nitrate and the fact that there are two of them to figure out that cobalt must have a charge of +2. Okay? And then in our second compound, we have ammonium, which is +1, and carbonate, which is -2. So when cobalt and carbonate combine, I just need one of each. And when ammonium and nitrate combine, again, I just need one of each. Okay, try the next 4, and then we can check your answers. Okay, so the first 3 of those you probably didn't have too much trouble with, but I want to look at the last one because that tends to give people a lot of trouble. So magnesium nitrate, again, if I just take the time to write the charges, it's not so bad. Magnesium has a charge of +2, nitrate is -1, aluminum is +3, and phosphate is -3. So when magnesium combines with phosphate, I need 3 magnesiums and 2 phosphates. When aluminum combines with nitrate, sorry, just had to fix a typo really quick. When aluminum combines with nitrate, I need 3 nitrates to balance out 1 aluminum. So it'd be AlNO3, 3. Okay, so we have a special type of double replacement reaction called neutralization. And in a neutralization reaction, it contains an acid and a base, and it always produces water and a salt. And when we say a salt, we don't necessarily mean sodium chloride, we really mean an ionic compound. Acids typically have H+, and bases usually have hydroxide, which come together to make water. Now, they both have hydrogen in them, so sometimes people have a little bit of trouble identifying the acid. But remember, acids have hydrogen as a cation. So that means that the formula will start with a hydrogen. So our first is HCl and NaOH. So HCl is hydrochloric acid, which you can recognize because it starts with that hydrogen. And this is sodium hydroxide, which is a base. In the double replacement reaction, the hydrogen combines with the hydroxide to make water, and the sodium and the chloride combine to make sodium chloride. One more example would be sulfuric acid and magnesium hydroxide. The hydrogen and the hydroxide come together to make water, and then we make magnesium sulfate. We have another special type of reaction, which we call a redox reaction. So redox is short for reduction and oxidation. Now we know that elements have multiple oxidation states. We learned that in Unit 4 when we were talking about transition metals and how they can have multiple different charges. But really, any element can have multiple oxidation states, because even ones like magnesium, for example, that only have one possible charge, when it's an element on its own, like solid magnesium metal, and it has no charge, it has an oxidation state of 0. So any element can have multiple oxidation states, although a lot of times one of them is just 0. So a redox reaction occurs when one or more elements experiences a change in oxidation state. 2 ways to remember the difference between oxidation and reduction. One is oil rig. Oxidation is loss of electrons, reduction is gain of electrons. And the other is Leo the lion says grr. Leo means loss of electrons is oxidation. Grr means gain of electrons is reduction. So, you can usually recognize a change in oxidation state when I have an element by itself, so not in a compound on one side of the equation, so it has an oxidation state of 0, and combined in a compound on the other side, so it has a non-zero oxidation state. So what that means is that synthesis, decomposition, single replacement, and combustion are all examples of redox reactions. The only type that isn't is double replacement. And if you think about the way that we predicted the products, that makes sense because we carried over the charges from the reactant to the product side. Now, what we're really going to look at with these are half reactions. So these just show part of the overall equation, either the oxidation or the reduction. So, if our overall equation is the reaction of iron with copper ions to make iron ions and solid copper, the oxidation process is when iron loses 3 electrons to form iron plus 3, and the reduction process is when copper ions gain electrons to form solid copper. So really, all you need to be able to do is to identify each half reaction as oxidation or reduction. So when we look at the first one, magnesium ions are gaining electrons, so it's an example of reduction. In the second, Neutral silver is losing an electron to form silver ions, so it's oxidation. So really, if you just look at the placement of electrons in these half reactions, it's fairly easy to identify whether it's oxidation or reduction. If the electrons are on the reactant side, that means they're being gained, so it's reduction. If they're on the product side, that means they're being lost, and so it's oxidation. All right, so try the next 3 and then check your answers. Okay, and again, it's completely based on the placement of electrons. All right, so a little bit of extra practice. Take a moment, pause, and identify the type of each of these reactions, and then you'll be able to check your answers. Okay, here are the answers for those. And for the most part, people do pretty well with this. It tends to be in the product prediction that people have a little bit of trouble. All right, now, for the product prediction, there are going to be 6 that you're going to have to do on the test, and that's because there's 2 single replacements. One of them is no reaction, and one of them occurs. So I would start by finding the combustion and predicting that product, getting that out of the way because those products are easy, then do the single replacements, and then do everything else. And you have an activity series attached to your homework, and on the test you'll be given one. All right, so pause, try these, and then check your answers. All right, so the reason that number 9 is no reaction is that copper is less reactive than magnesium, so it cannot replace it. Zinc is more reactive than silver, so it can. Okay, so bring questions to class, do the homework, and make sure you get a lot of practice with this.